All right, welcome Physics 11 to this week's lesson on circuits. This is lesson number 3, and today we're going to be learning about Kirchhoff's circuit laws. So, just to recap our last assignment, make sure we're all starting off at the right point. I just want to summarize what we learned in the last assignment. So last assignment, you had an activity to do, which was to build a circuit, and essentially there's two things I wanted you to take away from this. So number one, with this assignment was measuring voltage across a number of cells. So we know that each of these is a 9-volt cell, and so you can see this one's 9 volts, this one's 9 volts, here, etc. But when you add them up together, you just add the voltages all together. So two 9 volts in a row, two 9-volt batteries in a row gives you 18 volts, three 9-volt batteries in a row gives you 27 volts. Okay, that's fairly straightforward. And then we looked at a series circuit like the one we have up above here, where we have an ammeter, voltmeter, and 3 bulbs. And what I wanted you to take away from that is once we close this switch here, we're going to see that there is 0.3 volts of current that's transferring. Now, one thing I want to point out, not the most important point, but when you're setting up a voltmeter, the correct way to do that is where the black piece here, this black probe here, goes to where the current goes in. So there's a saying, this is called the anode, which is the negative part of a battery, but it's basically, anode means where the current goes into device. So there's this note down here, acid is a way to remember that. Anode current goes into device, and that's going to be the black piece here. So what we can see is across this battery, there is actually, I should be specific, I should say this is a cell. So a battery is when you have two or more cells joined together. So across this cell, the voltage is 9 volts. So what that's really saying is 9 volts essentially means 9 joules per coulomb. So if we think of these arrows as being 1 coulomb of charge, which is approximately the right speed for what we're looking at here. So we can see here approximately every 3 seconds, we have another arrow past the same point. So we have 9 joules of energy given to each of these coulombs of charge. Now, as this coulomb of charge moves from the cell where it now has 9 joules of energy, it's going to lose some of those joules of energy as it goes through these 3 light bulbs here. Now, we can see that in total each of these gained 9 joules, and in fact if we were going to look at these 3 cells, we'll notice that as it goes across this 3 cells, remember anode is where the black one goes at the beginning, we can see that the voltage from start to finish across the 3 bulbs is going to be 9 volts, or 9 joules per coulomb, meaning each of these arrows is going to lose the 9 joules that it got. And this is basically tied to the idea of conservation of energy. The cell gives it energy, gives each of these coulombs of charge 9 joules of energy, and the bulbs take away that energy. So it's converted from chemical energy in the cell into electrical energy, and then as it goes through the bulbs, that's going to be converted into light energy and heat energy mostly. Now, if we were to look at the individual light bulbs, we can see here, across this light bulb, they lose 3 joules per coulomb, or the potential difference is 3 volts. Across this one here, they lose another 3 joules, and across this one here, they lose another 3 joules. So each of these 3 components, these are all identical light bulbs, they're going to lose 3 joules per coulomb. So that was the main circuit that we saw. Now, an analogy that I like to use, just to kind of give you a bit more visual way of interpreting this, is think of this as if you've ever gone to the PNE and you've ever seen the log ride. The log ride looks something like this, where you go up the log ride here, and then you drop down the log ride at the bottom. So of course they have a bit more complexity to that, but this is just the most basic circuit here. So if we think of this as a path for those logs to travel. So imagine one of these logs is traveling up here, you're sitting in there, you're having a great time. This is like 1 coulomb of charge. Now, as this goes up here, it's gaining potential energy. Now, in the water slide, this is gaining gravitational potential. In a circuit, this is going to gain electrical potential energy. So as this coulomb goes up here, this is like a battery. The battery gives it some potential energy, and as it drops down, this could be like our light bulb. right? So as it goes down the light bulb, it's going to use that energy. And we have to see for a complete circuit that whatever it gains, so let's say this is 9 volts, so that means that this Coulomb is going to gain 9 joules of energy. As it drops down across here, it's going to lose 9 joules of energy. Now, if we have a circuit that, let's say it's a bit more complicated, instead of having just one single drop, let's say it drops it twice. Oops. So it's dropping it twice, and here's bulb number 1, and here's bulb number 2. In this case here, if these were identical bulbs, or if they were identical drops in this log ride, or if they were identical bulbs in a circuit, you can see that they would both lose 4.5 joules of energy for every Coulomb of charge that goes through there. So it goes through here and drops across each of these bulbs, and it's going to lose some of that energy each time it drops. So just to summarize what we have seen here. So number 1, voltage adds across cells. That's one important point. We saw, like, again, 2 9-volt batteries gives you 18 volts. And in a circuit, the PD gained across the cells. Now, PD is just short for potential difference. In a circuit, PD gained across cells is lost across components. Now, I'm going to change the word components to loads. So a load in a circuit just means something that has taken energy out of a system. So it could be a light bulb, could be a motor, could be a heater, could be anything that's going to take energy away. So it's going to be lost across the loads. And so essentially what we're saying is total voltage gained equals total voltage, or PD, lost. Okay, so that's what we need to know for potential difference. And again, this is all related to series circuits. Now for current, we saw this 2 weeks ago, in fact, that the current is the same at all points. So if we look back here, we can see that you can't have a different current at one point than the other. Let's say every second 10 of these carts, 10 of these coulombs ends up going to here, but every second only one of them goes down here. Well, you can quickly see that we're going to very quickly build up a huge amount of charge. If 10 of them are arriving here every second, and only one of them is leaving here every second, that just means we're going to get a massive pileup of these carts, or of these logs, or of these charges building up at one point of the circuit. We know that charges repel each other, so the electrons would all push themselves apart. It just can't be done that the current is going to be different at one point than the other. It's not possible. So that's the main takeaway for current. Now for resistance, we sort of have to look at this indirectly. So if we look at this circuit here, we have 9 volts and we have 0.3 amps. And so we need to indirectly figure out our resistance. We don't have a resistance meter or an ohm meter, although those do exist. We don't have an ohm meter here. All we have is a voltmeter and an ammeter. So if we look here, we have 9 volts and we have 0.3 amps. Now I've rearranged this equation here. So we have V equals IR. If we rearrange that to find R, it's just going to be V divided by I. So in this case here, V divided by I is going to be 9 divided by 0.3. And if we do the math on that, 9 divided by 0.3, it gives us 30. So the total resistance in this circuit is 30. Well, that's interesting because we have 3 10-ohm bulbs. So what do you think we might summarize that as in terms of our resistance? Well, 3 10-ohm resistors in series gives us 30 ohms. So 3 times 10-ohm resistors in series is the same as one 30 ohm resistor. And so, therefore, what we can determine here is that total resistance, and again, this is in series, equals sum of individual resistors. So these were all three 10 ohm resistors, but if I had a 10 ohm and a 50 ohm, my total resistance would be 60 ohms in that case for a series circuit. Okay, so now let's take a look, and we're going to look at a parallel circuit. How does this work for parallel circuits? And I've built this example here, and by coincidence, look at here, it's the same circuit. What we have here is we have three different branches. And with these three different branches here, we have got, they're all closed right now with the circuit. Well, you got a 10 volt battery and a 10 ohm resistor. So if I close this switch, basically if I close just this one switch, this is acting like a series circuit. There's no other loops. All the other loops are broken because the switches are open. And so I'm just going to have this one loop. And so we can hopefully figure out what the current's going to be. And so if this is 10 volts and 10 ohms, if we look at our equation in the bottom corner here, I equals V over R equals 10 divided by 10, which we know is going to be 1. So when I close this switch, sure enough, I've got 1 amp here, and because it's a series circuit, it's going to be the same current everywhere. So it's 1 amp here before the battery and 1 amp here after the battery. Okay. So now we're going to try this out with closing a second branch of the switch here. Now before I do that, what I would like you to do is think about, there's 4 meter readings that we have to worry about once I close this switch. There's going to be this ammeter reading up here in the top left, this ammeter reading, and this ammeter reading. So in just a moment, as well as this voltage reading here, potential difference reading. And just a reminder, we can see here that the voltage, it gained 10 volts here, so it's plus 10 volts as it goes through the cell, and as it goes through the light bulb, it's minus 10 volts. It lost each of these arrows, each of these coulombs of charge, lost 10 joules of energy. So it went through the battery, and this little guy here gained 10 joules of energy, and as it carried on here, it lost 10 joules of energy when it went across the bulb, so that it starts at the same place it finishes at the same place that it started. So pause the video now and try and guess what these 3 ammeter readings and the voltmeter reading will read after I close this switch. Okay, hopefully you've had some time to think about it. Now let's just close the switch and we'll see what happens. So here's what happened. This ammeter reading was still 1 amp. This ammeter reading, though, this new one down here, the second one, is also 1 amp. And this total ammeter reading here is 2 amps. Now, if we look at the voltmeter reading, it's negative 10 volts here. And in fact, if we look down here, we're going to see it's also negative 10 volts. So what is this telling us? There's 3 things that we should be thinking about here. So we know that this battery gives this single arrow up here 10 joules of energy. Now, this has 10 joules of energy. Now, when it comes down to this junction here, it may turn left here. Oh, it did. And so it's going down this path here, and it still has 10 joules of energy, and it's still going to go through here. And as it goes through here with 10 joules of energy, it loses it as it goes through the bulb, so it's back to 0 again before going back to here. Now, some of these arrows are going to go down this path here, and as it goes down this path here, it still has 10 joules of energy, and again, it's going to lose those 10 joules of energy before going back to the battery. So what we can see here is that it doesn't matter which path it takes, this arrow, or this coulomb of charge, is going to lose that 10 joules if it goes down path number 1 or path number 2. It has to lose 10 joules in order to bring it back to 0 again before it enters the battery. So that's about the potential difference, why it's going to be the same in both branches. Now for current, we can see here that if we have 10 joules of potential energy, so our V is 10, and our resistance is 10 ohms, then I is going to be equal to V over R is going to equal 10 divided by 10, which is going to equal 1 amp. So there's going to be 1 amp traveling through this branch here. And the same thing for this second branch here. Again, 10 joules of potential energy per coulomb, or 10 volts. The voltage is 10. The resistance is 10. So overall, we're going to have a current of 1 amp going through this bulb. And so when we add both of these together, we're going to get 2 amps. I'm going to stop this for a second and just want you to think about an analogy that's often used when describing current going through parallel circuits. Imagine this is like a road. Now, right here, from this path from here onwards to here, there's no resistance at all. So when there's no resistance, it means current can travel as fast as it would like to. However, as this traffic, as these cars, each of these cars or arrows or coulombs of charge, as it gets to this point here, there's a bit of a traffic jam on this road here. And so we can see that it's slowing down the traffic. And because the traffic is essentially bumper to bumper the whole way, if the traffic is slowed down here, it has to be slowed down here as well. Slowed down everywhere, which is why only 1 car per second can drive around this loop here. We can only have a current of 1 amp, or we can think of it that 1 car per second can get onto the highway, because it's going on this one single loop, and there's a traffic jam here, and that kind of affects everything. Now, if you have a traffic jam and there's only one path for all these cars to drive along, well, what happens if I open up another path? What happens if I open up another road? Well, now, even though this road has some resistance, there is some traffic here with this second light bulb here, we can still see that 1 car can drive down this road per second, and 1 car can drive down this road per second. So once they join the highway at the end here, and there's no traffic on the highway, they can have all 2 amps, or 2 cars per second driving overall. One's going down this first road, one's going down the second road. So think about that analogy. Now, I'm going to ask you to pause the video in a moment, but before you do, I want you to notice that these are both 10 ohm resistors, and this is a 100 ohm resistor. So it has 10 times as much resistance as the other two. So what I want you to think about is I want you to think about the meter readings for all 5 of these meters. So that's these 4 ammeters, 1, 2, 3, 4, as well as this voltmeter, when I close this bottom switch here. So if calculations are still throwing you off, it's fairly straightforward. Again, like total current for any component or for a whole circuit, either way, is going to be V over R. And so in this case here, you can try and figure out what this current's going to be, this current, and then subsequently this current, and also think about the voltage. So pause the video now, think about those 5 meter readings before you come back. Okay, hopefully you've had a chance to think about that, and let's go ahead and close this switch. So we've closed the switch. Now this is 100 ohms. So like we said, it's really 10 times more resistance than this. And so if each of these roads can have 1 car driving per second, the traffic is 10 times as bad. So we can only have 0.1 car per second, which is what this ammeter reading is saying. There's 1/10 of the amount of current because there's 10 times as much resistance. But nonetheless, there are still more cars that can travel. 1 car can travel down this road per second, 1 car can travel down this road per second, and even though the traffic is bad, there's still 0.1 cars that can travel down this road per second. So that's why this ammeter reading is actually going to increase. So it was 2 before we switched, before we closed the switch, and now it's 2.1. That current has gone up by a little bit because we've opened up 1 more road for it to travel on. So that would explain the 2.1, the 1, the 1, and the 0.1. And what would the voltmeter reading be across this component? Well, it should be no surprise that it's still going to be negative 10 volts, because even though these arrows are moving more slowly, each of these arrows currently has 10 joules of energy per coulomb, or 10 volts. And so as it goes across the light bulb, it's going to lose that 10 joules no matter what. Okay, so there's a lot to unpack here. Let's go back to our notes and try and summarize that. So for the current in a parallel circuit, the total current is a constant, but it can be split among different branches. So we saw this before. Current can be split between branches. Losing the ability to spell today. Okay, so it can be split between branches. We actually saw that in week 1 as well. And if we look here for when there was two resistors, I'm going to do this in two different colors. So two branches, we had two branches, total current equals 2 amps. I total equals 2 amps. And that was because it was equal to I1 plus I2. So I'm referring to this as I1, I2, I3, and this is I total. So it's going to equal I1 plus I2, because that was the two branches moving around through here. And so that was going to equal 1 amp, 1 amp, and that gives us 2 amps. Okay. When we had three branches, the I total is equal to 2.1 amps. And this is because it was equal to I1 plus I2 plus I3. And so that was going to be 1 plus 1 plus 0.1. That's going to give us our 2.1. So that was what we had for our currents. Now for potential difference, the main thing to keep in mind is that it was the same in each branch. So what I'm going to say there is each coulomb, let's go back to blue for our notes, each coulomb of charge I can close this now. Each coulomb of charge loses the same energy, same amount of energy, regardless of the path taken. Okay, so if it went across branch 1, branch 2, or branch 3, it was still going to lose 10 joules of energy per coulomb, where the potential difference was 10 volts. Now, when we had 2, again, 2 or 3, either case was the same thing. The PD, or let's just call it voltage, so voltage total equals voltage cell equals V1 equals V2 equals V3, and these were all equal to 10 volts. So the cell gave it 10. If it went down this branch, it lost 10. This branch lost 10. This branch lost 10. So that was what it was for potential difference. Now let's go back to thinking about resistance for a moment. So if we think about our traffic analogy, when we open up another street, more current is able to flow. Now, resistance is kind of defined as how difficult it is for current to flow. So we can see that if we have more and more resistance, we're going to have less and less current flowing. But the opposite is also true. If we have more and more current, like we do when other branches are open, we're having more current each time we add a branch. What does that mean for our resistance? Well, if less current means there's more resistance, then more current must mean that there's less resistance. So whenever we're adding a new branch here, what's actually happening is we are reducing the current. And that's true even for this third branch where the resistance was way higher. We've still lowered the resistance a small amount. And we can see that because overall there's more current flowing. There was 2, and now there's 2.1. So by adding another branch, we always are going to lower the resistance. Even if it's just by a little bit, it only went from 2 to 2.1, but nonetheless, there's still a tiny bit more current flowing, which means the resistance went down by a tiny bit. So the main takeaway here for resistance is that each branch added lowers the total resistance. So that's the main takeaway there. And we can calculate it as well. Remember our formula V equals IR, so R equals V over I. Now for two branches, the voltage was 10. So in this case here, it was going to equal 10, and the current was 2 amps, and therefore resistance was 5 ohms. Now for three branches, going to make sure this looks separate here. So this part here above the L line is for potential difference, and the part below it is for resistance. So for 3, we still have the same formula true. So the total voltage divided by the total current equals our total resistance. This is going to be 10 divided by 2.1, and this equals approximately 4.76 ohms. So with two resistors in parallel, 10 ohms each, the resistance was 5, which was half, you'll note. And then when we added one more branch here, it ended up being a tiny bit lower. The total resistance was 4.76 ohms. So we can confirm mathematically that it reduced. And we can also think about our analogy. If we open up a new road, no matter how bad the traffic is, there's still some traffic that's flowing. And so overall, more traffic is flowing. And that means that resistance has gone down. Okay, so we've, over the past 2 weeks, and what we've just seen today, is we've kind of made up our own rules. And these rules, although we've discovered them for ourselves, we can't take credit for it. These were discovered or kind of formalized by someone named Kirchhoff many, many years ago. So let's take a look at what these rules are. So for a series circuit, what we'll find is that for current, the current is the same at all points on the path. In the circuit. And as a formula, we can say IT equals I1 equals I2 equals I3, etc. So if we measure the current at any point, it's still going to be the same total current. Now for a parallel circuit, the charge can split between the different paths. Those coulombs can take path 1, path 2, path 3. And so therefore, we have this formula here. So IT equals I1 plus I2 plus I3, and where each current is a current for one branch. So this is the current going down branch 1 plus the current going down branch 2 plus the current going down branch 3. And Kirchhoff's law, Kirchhoff's current law, or as I like to call it, Kirchhoff's junction law, it's often called Kirchhoff's junction law, can just be stated as the sum of currents entering a junction equals the sum of currents leaving a junction. So there's kind of two scenarios. You can have one current branching into 2 or 3 or 4 other ones. So we have I1, I2, I3, and then we would say I1 equals I2 plus I3. In this case here, or another example would be you have these currents here. Let me change the color. So this current plus this current go to a junction, and this current leaves. So this is I1, I2, I3, and we can say I1 plus I2 equals I3. Obviously, it can be a bit more complex. You could have 2 going into 2, you could have 1 going into 3, you could have 3 going into 2, etc. But nonetheless, this is the same idea here. So no matter how many currents are going into it, how many currents are going out of it, this statement here, the sum of currents entering a junction equals the sum of currents entering or leaving a junction, that is always going to be true. Okay, now what about for voltage? So Kirchhoff's voltage law essentially states that the sum of potential differences in a circuit or in a loop, so this law is called the voltage law, but also often called the loop law, which is maybe a better description of it, says the sum of the potential differences in a circuit or in a loop must equal 0, oddly enough. And so this is essentially restating the law of conservation of energy. Right? So remember that an increase in the potential difference across the terminals of a cell or battery, and that there is a decrease in potential across a load. So again, remember load is like a resistor, light bulb, motor, etc. And these increases and drops must add up to 0. So what we're saying for a series circuit is that Vt is going to equal V1 plus V2 plus V3. And if we go back to this circuit, for example, that's what we're saying here, is it's 9 up, but then it's going to be 9 down, which is the same as saying it's 3 down plus the other 3 down plus the other 3 down. So that's what that's saying there for a series circuit. Vt equals V1 plus V2 plus V3. And so since there's only one path, you can see that it would be equal to the total drop across each resistor. So it's going to lose 3 in each of those for that previous example. Now for a parallel circuit, what we notice is that the potential difference is the same across each branch. So before entering this branch here, each of these coulombs has 10 joules of energy. So if it goes down this branch or this branch or this branch, either way, this coulomb of charge is going to lose 10 joules of energy, which is the same thing as saying that there's a potential difference of 10 volts or 10 joules per coulomb. So it's going to be the same across each branch. And so the formula for this is going to be Vt equals V1 equals V2 equals V3, and this is V number equals voltage for one branch. Okay. Now, Kirchhoff has these two laws. He's got the loop law for voltage, and he's got the junction law for current. He doesn't have a law, Kirchhoff doesn't have a law for resistance. We could do a big derivation to figure out the formula using Kirchhoff's law and Ohm's law, but let's just reason it out. And in fact, we've already done this here, so I'm just going to give us the answer. We already saw this in the first part of, or earlier in this video, and so we saw the total resistance is equal to R1 plus R2 plus R3, etc. Now, for a series circuit, the total resistance is the sum of the individual resistances. And since I must push its way through each resistor, that would make sense that the resistances are cumulative. If there's 3 traffic gems, it's going to be 3 times as hard for traffic to go through, for example. Now for a parallel circuit, I'm just going to show you the formula. Instead of doing a fancy derivation, I'm just going to show you what the formula is. And it's this right here. So we actually have to do 1 over the total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. And let's just try out, before we carry on, let's just look at the previous example. So in the previous example up on the first page, we had this picture here. So we had 10 ohms, 10 ohms, and 100 ohms. So if we do the 10 ohms, let's just look at this as an example. So 1 over the total resistance is going to be equal to 1 over 10 plus 1 over 10. I'm just doing the two circuits here. So this is going to be equal to 2/10, which is equal to 1 fifth. So this is our 1 over RT. And so if we take the inverse of both of these, we're going to get RT equals 5, which is what we found. Now, I'm going to show this on the calculator here for the previous one. Now, on the other example, we had a 10, a 10, and a 100. I'm going to make your life a little bit easier and just show you how to do this quite easily on your calculator. There we go. Okay, so we had 10 and 10 and 100, and we're going to find out what that resistance is. So the easiest way to do this is using brackets. So I'm going to say 10 to the power of negative 1, or 1 over 10, plus 10 inverse, or 1 over 10, plus 100 to the power of negative 1. Oops, missed a 0 in there. 100 to the power of negative 1. So now what I've got here, what this is saying is, I'm just going to draw this over here. This is going to be 1 over 10 plus 1 over 10 plus 1 over 100 is the same thing as writing here 10 to the negative 1 plus 10 to the negative 1 plus 100 to the negative 1. And if I put all of this in brackets, this is equal to 1 over RT, which is also equal to RT to the power of negative 1. So all I have to do now is take this total amount right here and then put this to the power of negative 1 itself. And that's going to give you my answer, which is 4.76, which is exactly what we calculated from looking at the voltage and current. But this is just confirming it another way. So if we want to calculate the total resistance, this might be the easiest way to do it on your calculator there. Okay, and we did know already that when we add resistors in parallel, the total resistance decreases. That's a major point that you need to understand. Okay, and again, this makes sense. Even if there are multiple paths, it's still going to be easier for current to flow, even if the other path has higher resistance. So I'm just going to quickly recap what we've learned here. So for voltage, in a series, Vt equals V1 plus V2 plus V3, and in parallel, Vt equals V1 equals V2 equals V3, and I'm going to say for each branch. Okay, when we look at current, we have I1 equals I2 equals I3 for series, and for parallel, I total equals I1 plus I2 plus I3 for each branch. We're saying the current in branch 1 plus the current in branch 2 plus the current in branch 3 gives us the total current traveling through that whole parallel series or parallel portion of a circuit. And lastly, we have resistance. And in this case here, RT equals R1 plus R2 plus R3, or for a parallel, 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. Okay, so that's it for this video. Now on the next video I have for this same week, I'm going to go over problem-solving strategies for these types of questions. You have all the theoretical knowledge that you need to carry on. We're going to go over some practical examples in the next video. I've split it up because this video is already long enough. So hopefully you've gained something. Hopefully you've gained ultimately a deeper understanding of how circuits work. And I will see you in the next video.